The Pennsylvania Railroad was the largest railroad in America. At its peak, it employed over 200,000 people. It moved more freight and more passengers than any other single company in the country. And in 1915, it decided to kill steam. Not slowly, not as a gradual transition that engineers could adjust to over years. The Pennsylvania Railroad's electrification of its New York City tunnel routes was sudden, decisive, and almost violent in its speed. Locomotives that had pulled the most important passenger trains in the country were pulled from service within weeks, replaced by electric motors that weighed a fraction of a steam engine and produced no smoke, no ash, no noise beyond a low electrical hum. The tunnels under Manhattan and the Hudson River had made the decision for them. Steam couldn't survive underground, not anymore. The problem existed before 1915. It existed since the first tunnel was dug. Steam locomotives produce smoke. Smoke requires ventilation. Tunnels don't ventilate easily. The longer the tunnel, the worse the problem. A short tunnel, half a mile, manageable. Crews open windows, hold their breath, endure. A tunnel 5 miles long, filled with coal smoke from a locomotive burning tons of fuel per hour, becomes a death trap. Carbon monoxide and sulfur dioxide accumulate faster than any ventilation system of the era could remove them. The Pennsylvania Railroad faced this problem directly when it built its terminal in Manhattan. Penn Station opened in 1910. Getting trains into the station meant crossing under the Hudson River and running beneath the streets of Manhattan. The tunnels were long. The traffic was heavy. Multiple trains per hour, each one pumping black smoke into enclosed stone passages. The air quality underground became dangerous almost immediately. Early solutions were primitive. Ventilation shafts were drilled at intervals along the tunnel routes. Fans pushed air through the passages. It helped. It didn't solve the problem. A steam locomotive moving through a tunnel at speed created its own wind, drawing smoke backward into the tunnel behind it. The physics were simple and unforgiving. More trains meant more smoke. More smoke meant worse air. Worse air meant danger to crews and passengers alike. The engineering department at Pennsylvania Railroad began studying electric traction in the early 1900s. The technology existed. Electric railways had operated in cities for decades. Trolleys, subway systems, commuter lines, all electric, all proven. The question wasn't whether electric locomotives could pull trains. They could. The question was whether they could pull the heaviest, fastest passenger trains in the country, the kind of trains the Pennsylvania Railroad was famous for. So the GG1 electric locomotive wouldn't come for another 20 years. In 1915, the railroad deployed a different design. The P5 A-class locomotives were heavy, boxy machines that looked nothing like the sleek steam engines they replaced. They were ugly by railroad standards. Engineers who had spent careers in the cab of a steam locomotive looked at them with something close to contempt. These were not the machines that had built the railroad. So they were machines that the railroad had chosen because the alternative was choking in a tunnel. Testing began in 1914. Electric locomotives were run through the Hudson River tunnels alongside steam power, comparing performance under identical conditions. The results were clear. Electric locomotives accelerated faster in the tunnels. They maintained speed more consistently. They produced no exhaust. They required less maintenance per mile than a steam engine burning coal. The economics favored electricity, and the safety data demanded it. The transition happened faster than anyone expected. By early 1915, the Pennsylvania Railroad had committed to full electrification of its tunnel routes. Steam locomotives were pulled from Manhattan tunnel service. Crews who had worked those routes for years were reassigned or retrained. Some refused. A few quit entirely, unwilling to operate machines that felt, to them, fundamentally wrong. A steam locomotive was alive in a way an electric motor was not. That you could hear it breathe, you could feel the heat from the firebox, you could smell the coal smoke and the hot iron. An electric locomotive was quiet, clean. Mechanical in a way that felt disconnected from the work it was doing. The workers who maintained the tunnels noticed the difference immediately. Air quality improved within days of steam being removed from the routes. Soot that had coated tunnel walls for years stopped accumulating. Some ventilation systems that had worked overtime for a decade suddenly had less work to do. The tunnels, for the first time since they were built, were breathable. Passengers noticed too, though their perspective was different. The ride itself changed. Steam locomotives produced a particular rhythm. The hammering of pistons, the hiss of valves, the occasional whistle echoing off tunnel walls. Electric locomotives were almost silent by comparison. A low hum, the click of switches, and the rush of air through the train cars. Some passengers found the quiet unsettling at first. They had grown accustomed to the sound of steam as a sign that the railroad was working, that power was being generated, that the machine beneath them was alive and functioning. The electrification of the Pennsylvania Railroad's tunnel routes did not end steam on American railroads. Steam locomotives continued to operate across the country for decades after 1915. Long-haul freight, rural passenger service, our branch lines far from major cities. All these continued with steam power well into the 1950s and beyond. What the Pennsylvania Railroad's decision did was demonstrate something important. Electric traction was not the future. It was already here. It worked. It was faster, cleaner, and in enclosed environments, fundamentally safer than anything steam could offer. Other railroads watched. Some followed quickly. The New York Central electrified its commuter routes. Regional railroads in the Northeast adopted electric power for their tunnel and urban segments. Others waited, skeptical that the technology could handle the weight and distance requirements of mainline service. They were right to be cautious. Electric locomotives in 1915 were powerful enough for tunnel routes and commuter runs, not yet capable of replacing steam on transcontinental lines. That capability would develop over the next 30 years, but it would develop slowly, unevenly, and not always where or when the industry expected. The Pennsylvania Railroad's electric locomotives served faithfully for decades. The P5A class was eventually replaced by the GG1, one of the most famous locomotives ever built. The GG1 entered service in 1935 and ran until 1974. It was fast, powerful, and reliable in a way that justified every skeptic's eventual conversion. The tunnels that had forced the transition in 1915 continued to operate, are carrying millions of passengers per year through passages that had once been filled with coal smoke and are now clean enough to breathe without discomfort. The men who refused to work electric locomotives in 1915 were not wrong to feel that something had changed. Something had. The relationship between a railroad and its power source shifted from something almost organic, coal burning, steam rising, iron moving, to something electrical, invisible, and fundamentally different in character. And the railroad didn't disappear. The trains didn't stop running. The tracks stayed where they were. What changed was the nature of the force that moved everything along them. In 1915, that change happened in a tunnel under Manhattan, and it happened faster than anyone working for the Pennsylvania Railroad had thought possible.